All right, this is short lecture 2. I'm Jim Wilson, and hopefully you have looked at lecture 1. So this particular one, we're going to look at, you need my laser pointer, bring it up. Okay, in this one, we're going to be looking at low-level convergence lines, as it's seen on the radar as reflectivity thin lines. And these are very important for nowcasting thunderstorms because these thin lines are often associated with the initiation of new storms, not just over the land, but over the lake. So we're going to look at these following convergence lines we're going to discuss: gust fronts, land breeze fronts, lake breeze fronts, and unknown boundaries. Okay, this is a slide of radar reflectivity slides showing a gust front, land breeze front, lake breeze front, and unknown. So you can see the gust front here, land breeze front here, lake breeze front here, faint, but it's there, and the unknown. Now, when we first started to look at data, we were very surprised that we could see convergence lines over the lake. This is a great surprise. Typically, we have not been able to see much in the way of clear air over water features. So this greatly increases the ability to nowcast thunderstorm intensity and winds over the lake, and greatly increase the ability to have an early warning system. Okay, the reason we can see these, as we learned in the first lecture, is the backscatting for the enormous number of insects you have over the Lake Victoria Basin. Okay, the first convergence line, which is the unknown one. We don't know where they came from. And there are many of these over the lake. We just don't know where they came from. But they're still very important because they initiate new storms, and they're very important to monitor where they are and how they're moving. Now, before we look at other convergence lines, we should ask ourselves the question, well, why? Why do we have these thin lines? Why are these thin lines showing up out in the clear air? Why are they there? Well, let's take a look and examine that. Okay, here we got the lake surface, and here we have two converging wind flows, and of course there'll be the resulting updraft. Okay, the reason is because often there's a convergence of insects here. We have these two flows meeting, so they're going to converge the number of insects there, and that'll increase the radar reflectivity. But there's a second reason. So in the updraft, the insects are, of course, being carried upward, but they resist. They resist being carried aloft. I guess they just don't want to get cold. I never asked one. But so this leads to a further increase in insects here because there's more coming in and going out. The rate of coming in and going out is different. So we get even a further increase. And then, of course, there's the third reason, and that's that this increased number of insects attracts more birds, more food. So all this leads to an increase in updraft regions. In updraft regions, there'll be higher reflectivities, and that's why we see the thin line out in the clear air. Okay, moving on to the land breeze front. Okay, we have a land breeze front that we see out over the lake. This is from Mwanza. We have the cool airflow off the land nighttime, and that creates this thin line of convergence. Now let's take a look at a schematic of what really is going on here. So here we have the cool land at night. So the air flows off that land over the water, and then we'll have our land breeze front out here. And if you look at what's going on, you got this air coming out, then you'll have air rising up, can form the clouds and storms even, and it gives you this circulation like that. Now, let's look at the lake breeze front, Okay, so now this one's from NTIBI. So here it's just the opposite situation, and now they got the airflow is coming off the lake, and forming a thin line. Usually with the lake breeze front, the thin line is very faint. It shows up much better in Doppler velocity, but being daytime, we have the visible satellite, which nicely can show a line of cumulus clouds with it. And just by monitoring the satellite, you can get a good feel of how these clouds are building and forming storms. Now let's look at the schematic for the lake breeze front. So we have the cool air is daytime. We have the cool air coming off the lake, going over the warm land. So you have an updraft here, and you have that basic circulation, but in the updraft you can form clouds and storms. Okay, our last one is the gust front. And as we've seen, we have the storms here. We have yellow arrows showing the outflow of cool air from these storms, forming our thin line, our gust front. Now, if we go over here and look at the schematic, we have the thunderstorms. Imagine these are the thunderstorms. And we have the cool air coming down from evaporation of the rain. And we get the cool air coming out. And of course, here will be the leading edge is our gust front. And with the warm air, we'll then ride up over this cool air, forming the updraft to the storm. So here we have a radar reflectivity image of a gust front, as we just saw. So, again, here's the arrow showing the cold air coming out and forming the thin line. But let's look at Doppler velocity. Well, Doppler velocity, we have our Doppler velocity convergent feature, which we studied in lecture 1. And that is that we have the flow going away from the radar pretty strong, and then all of a sudden flow coming towards the radar. So we must have a good convergence zone here. And this is precisely where this thin line is in reflectivity. Now, these winds, you see, can be pretty strong. Here we got 20 to 25 in here. Well, let's go look at a schematic then. So imagine we're looking at these thunderstorms. And so you'll have coming out, you have the strong outflow from these storms. And we saw it could be 50, 20, 25 meters per second, or of course, in some cases, much larger. And so where that wind is coming out over the lake real strong, it can generate large waves. And of course, those waves are not, it could be disastrous to those small boats. So in summary, we've seen in this short lecture, first thing, that we see convergence lines are common. They're common over Lake Victoria. So this provides great potential that they'll be very useful for nowcasting thunderstorms over the lake. And we're going to look at this a lot in subsequent lectures. Our second point was that we did see convergence lines that were from gust fronts, sea breeze fronts, land breeze fronts, and then all the unknown ones. Our third point was that insects and birds are very plentiful in the Lake Territory, and that's all year long. So the radar returns from biological scatters makes it possible to observe the winds and convergence in the clear air. We don't need precipitation, just in the clear air. And fourth thing, we saw that the sea breeze front was fairly difficult to detect in the radar reflectivity over the land breeze front. While we could see a little better in the Doppler velocity, it was the visible satellite, being daytime, that was very useful for monitoring the clouds associated with the sea breeze front. So now, I missed the discussion that in the future lectures, we're going to be monitoring these convergence lines as very successful nowcasting. And, to do this monitoring of the convergence line, it requires almost continuous monitoring of the radar data and use of time-lapse radar imagery. So it takes this continuous monitoring and looking at time-lapse to really do a good job of the nowcasting. So here we are, we're to the quiz point. And as in previous lecture, there will be slides with a question that then are followed by the answers. And so in this case, like similar to the first quiz, there's going to be 2 slides with questions. And then after each question slide, there'll be the answer slide with explanation. And also remember, when you get to the question slide, pause it, and on a piece of paper, answer the questions, and then you can easily go forward and backwards with the buttons to look at things you didn't understand as well the first time. So at this point, you're going to take the quiz, and I'm going to leave you until short lecture 3. So good luck with the quiz.